Hi, this is Mrs. LaBarbera. This is AP Physics Mechanics C. This here is an example of how to apply Newton's laws to solve problems. A block of mass mb is being pulled up a ramp by a hanging object of mass mh as shown. The blocks are attached to each other by a light string that passes over a pulley of negligible mass and friction. Both the block and the hanging object are moving at constant speed, and the angle of the ramp with the horizontal is theta. The coefficient of kinetic friction between the block and the ramp is mu k. Question A. On the diagram on the dots below, which represent the block and the hanging object, draw and label the forces, not components, that act on the block MB and the hanging object MH. Each force must be represented by a distinct arrow starting on and pointing away from the appropriate dot. So on the block MB, we know there's normal force perpendicular to the incline, there's gravity goes straight down, there is tension along the incline, there is also friction opposite of V. So those are the forces on MB. And on the hanging object, just two forces. Now this T and MHG has to be the same because this object MH is moving with constant speed. And this T on the MH and T on the MB are also has to be the same because it is the same string. And again, all the forces on MB should be canceling out. So appropriate length you should have. B. Derive an expression for the mass mh of the hanging object. Express your answer in terms of mb, theta, mu k, and the physical constants as appropriate. If you need to draw anything other than what you have shown in part A to assist in your solution, use the space below. Do not add anything to the figure in part A. So that's one thing is very important is when you draw free body diagrams, never draw the component force. So if you needed to draw component force, just simply draw another diagram. So everything on this object on the incline, we know we have our coordinate is parallel to the incline and perpendicular to the incline. Only this mg is does not lie on your coordinates. So we need to change MBG to the MBG parallel and MBG perpendicular components. So in this case, all the forces are acting along the coordinates. It's much easier for us to figure out the forces. So for example, on the MB, there are two equations. So in the parallel direction, tension should be equals to force of friction plus mbg sine theta. So force of friction is going down, mbg sine theta is also going down. And force of friction is just mu k times normal force plus mbg sine theta. That's in the parallel direction. In perpendicular direction, we have n, the normal force. Normal force should be equals to the perpendicular component of the weight. That's are the two equations for the object MB and one equation for the object of MH. The downward gravity should be equal to upward T. Now, we combine these three equations together. This is what we had. T we can change into MHG. And F is mu K times N. Mu K, N, we can substitute N with MB G cosine theta plus the other term. In this equation, you can see all the G cancels out. And MB can be factoring out. So MH equals MB times the first term you have left is mu K cosine theta plus sine theta. Another part. It is determined that MB equals to 2 kilograms, theta equals to 30 degrees, and mu K is 0.1. While the blocks is moving up the ramp and the hanging object is moving downward, the string is suddenly cut. Question C. Part 1. Calculate magnitude of the acceleration of the block at B immediately after the string is cut. When the string is cut, what are the forces acting on MB? You just have three forces left: the normal force and friction plus the gravity. Gravity has two parts: the parallel parts, which is MBG sine theta, and perpendicular parts, which is MBG cosine theta. So we know N should be equal to mbg cosine theta. That is because mb is not moving along the perpendicular direction. So it only moves along the parallel direction. So if we take the direction of v as positive, going up as positive, now MBA, that's a net force, should be the sum of all the forces. Sum of all the forces in the horizontal direction is just negative MBG sine theta minus mu k. The friction is mu k MBG cosine theta. So in this equation, all the MB get cancels, so you'll have A equals negative G sine theta plus mu K cosine theta. Simply substitute your G, your theta, and your mu K, you will have A equals negative 5.75 meters per second squared. What does this negative mean? This negative means the direction of acceleration is down the ramp. That's what it means, because we take the direction V as positive. So if going up is positive, going down must be negative. Number 3, determine the magnitude of the acceleration of the hanging object mh immediately after the string is cut. After the string is cut, the only force on mh is gravity. Hence, the acceleration is gravitational acceleration. Its acceleration is just 9.8 meters per second squared. This negative means it's going downward, it's in free fall. Last part, assume the block is moving up at a ramp of 2 meters per second when the string is cut. Calculate how far the block travels up the ramp from the time the string is cut until the block stops. So here is your initial speed. When the block stops, that's your final speed. What else do you know? You know the acceleration. So once you know 3 things, you can find all the other kinematic quantities. Assume there is sufficient distance to stop. So what you need to find the distance. How far does it travel up? Since you don't have time, so we use timeless equation. In this equation, we know V, that's a final velocity equals to 0. V naught is 2 meters per second, and A is negative 5.75. So we're trying to find delta D. So delta D is equals to V squared minus V naught squared divided by 2A. Simply substitute all the given quantities. You should have 0.348 meters. That's it. I hope it helps. Thanks for watching.